Greetings and welcome to a new video. In this video we will discuss the basic concept of a differential amplifier and why we need that to reduce or eliminate our ripple in our circuit. So we will see that conceptually and also discuss several examples using simulations in SPICE. Okay. So why do we have a differential signal? So why do we need that? Let's start first with that. You have here, for example, an rectifier circuit. First we have here an AC signal and it will be rectified, and this capacitor C1 will be then used to filter that rectified signal, and then you need to use that as our DC source for our amplifier here, which is our common emitter amplifier. We have here our microphone and the C2 is here to AC coupling that microphone signal. And we have also here the biasing, which is not shown here in detail, and we will measure here at the collector node, and that will be our output voltage. And what happens if you have a ripple or kind of a distortion in your VCC, which is our DC power supply for our circuit? Well, we assume that our DC power supply VCC is a constant. So let's say it is a constant value, let's say 10 volts. Well, in practice, it has some ripple in it, and that might cause some problems at the output. And that problem is actually that we have two separate paths that goes to the output. So we can identify, in this case, two components in this amplifier, which is then a common emitter amplifier as this example. But the same applies also for the common source amplifier. So the amplified form of this microphone signal will be then go at this node, the collector. That's one. That's also what we need. But there's also a ripple present because of this VCC, and that will be also passing through that in the output node, which is again VO. So in more detail, you see here the VO, which is a signal where we have the voice signal. For example, from the microphone, we want to amplify, but there's also this ripple because of this ripple in the VCC, and that's not what we want. So the blue signal is what we want, that is the information, but the ripple, this red one, is also coming into this output node, and that will then disturb your signal. So the problem is a ripple present on this VCC in this case, so how can we now eliminate that ripple? That is our objective. Okay, now we can modify the amplifier topology such that the output voltage is insensitive to VCC. So what is then the possible topology for this? So what will then happen if the output voltage is not referred to ground? Maybe we can ask this question. If you look at this node, it is referred to ground. So we measure here with respect to ground. That is actually our reference. Now we might get a solution if we do not do that. So let's check that in more detail. So we can measure with respect to another point which has the same change here because of the ripple, and that might then eliminate that. Now let's see that in more detail. So it is possible to eliminate the ripple and then get a net output voltage. Here we have actually a duplicate of this amplifier circuit. You see that actually here. And again, our microphone with this AC coupled capacitor. And I have now here mirrored, this is the differential operation actually. And you see here the ripple of this VCC again, and that ripple will be again going to this node and also to that node. So this is exact same ripple. So what happens here? Well, if we now designate this output voltage VO1, that's the node, and another one is here VO2. The difference between that is in our differential mode output, which is then our VOD. Now VOD is, looking at that, is the VO1 minus the VO2. So we can say, what's the net output voltage? First we start with the VO1. That's actually the voltage here, which is the amplified version from the microphone. So the VI times the amplification AD, which is our differential mode gain, just from the transistor Q1. Plus there will be some ripple voltage because of this ripple from the VCC again. That is what we call the VR. Now for the VO2, since there's no amplification here, it's just a biasing, so there's AC coupled, so it is actually here in this case ground. We will have only here the VR, which is our ripple. Now, if we now take this together and then use the fact that the VOD is VO1 minus VO2, that's what you see here, that will then give us this expression. Now you'll see here, indeed, this is not respect to ground. In this case, this is respect to ground, but this one is now actually a floating value, which is between these 2 points. And now you see here the VR minus VR. So you get actually our ripple and minus ripple, and that will be then eliminated. So our VOD, which is our differential mode output voltage, is now the differential mode gain times the input voltages are information only, and not anymore the ripple from the power supply VCC. So we have eliminated our ripple, and this is exactly what we wanted. So our differential mode topology, our amplifier topology, will solve the problem of our ripple because of this VCC. Okay. Let's see that in more detail. We have an example here, which is in the simulator, in the Tina TI Spice. I have here several plots, and those plots are from this circuit. You see here, again, our differential pair. The BGTs here, Q1 and Q2. This one is again grounded. And this biasing here, which is not shown in more detail in the previous examples and the slides, we have here managed that using this DC current. So this tail current will now manage and then create here the required biasing. But before going into the detail, my objective and my goal is to show you what happens if there is a ripple in this VCC. So I have here again the resistors, and I also measure here the VO1 and VO2, and also between those two, which is then from the left to right side. Okay, you see here the VCC, which has a value of 20 volts, which is now in this case DC constant 20 volts. And I also have here VR in series to reflect that ripple. And that is a sine wave, which is in this case 4 volts peak. You see that exactly here. And it has a very high frequency compared to the input signal, in this case the VID. So we will have here a summation of the DC quantity, 20 volts, plus this 4 volts peak for our sine wave with specific frequency. So that will be exactly put in here. So what happens now? So let's go in detail. This is now the differential mode input signal, which is our blue signal, which is 10 millivolts peak, which is going actually in this direction. We also have the expressions or the plots for our currents IC1 and IC2. Those are actually quite clean. You also see here the VCC, which is our power supply VCC here, and that is in this case indeed 20 and going up to 24 and going down to 16. So we have here indeed 4 volts up and 4 volts down because of this ripple voltage. Now you see here, if you look at that, indeed that we have 8 volts peak ripple in our power supply. And because of that, you see here the VO1 and VO2 is not a nice sine wave, which is amplified. It is amplified, but it is quite distorted because of this ripple. So single-ended output voltages will contain that ripple. Now VO1 and VO2 will then have that ripple, but if you look at the VOD, which is this red curve, that will be then actually free of that ripple. So it doesn't contain that ripple, which is actually nice. So you actually have ripple minus ripple, a ripple is gone, which is perfect. So this is exactly what we want and exactly the solution we are actually looking for. And it is now also shown here using this example in the simulations in Spice. Okay. The next one is about the configuration. So let me also discuss that a little bit more detail. So this is our differential amplifier. We have here 2 inputs, 1 and 2, and we have here also 2 signals, VI1 and VI2. This one is a non-inverting input, and this is the inverting input, like in the operational amplifier. And we have here our output, and we can designate it again as VO1 and VO2. Now this differential mode output voltage is then given by the VOD. We have already discussed that, which is the VO1 minus VO2. And we can now calculate that then using the difference between these 2 input values, VI1 and VI2, times the differential mode gain AD. Okay, so the input sources, as shown here, VI1 and VI2, we can transform that or represent that in a different way, where you see the common mode and the differential mode signals, or differential mode and common mode sources. So the original sources, which are VI1 and VI2, can be replaced by an equivalent system of sources. This is handy. We will see that shortly why this is handy. So we see now here 2 different signals, VIC and VID. Well, this is now the VI1 again, and this is now VI2 again. That is still the same, because these two nodes are exact same as these two nodes, also these two nodes. So differential mode input signal, VID, is the difference of the VI1 and the VI2. So that's just the VI1 minus VI2. And that is then, if you look at this expression, can be then written like AD times VID, which is then VOD. Our common mode input signal is then the average of the input signals, VI1 plus VI2 over 2. So that's the reason for using those two sources in our system. And if I now call this equation number 1 as this equation number 2, I can also rewrite this equation number 2 by multiplying the left and the right hand side by 2. I would like to show you something, and I call this equation number 3, because I would like to show you that this node voltage here has an expression, also this node voltage expression here, which includes this common mode input and the differential mode input voltages. So let's do that. So we will add this equation number 1 to this equation number 3. So what will you have? Now you will have then, you see the VI1 minus VI2 plus this one, so you will lose the VI2s because this is the minus, this is the plus, so you get 2 times VI1, that's shown on the left side. And you have the VID plus the 2 times VIC. Now if I now divide by 2, I get this expression for the VI1, which is then VIC plus the VID over 2, which is exactly here. So you see from here to ground, you measure VID over 2 plus the common mode input voltage, which is actually shown here. So this transformation is actually again proven by this expression using the equations here. And similarly, we can subtract here the equation number 1 from equation number 3. So I do 3 minus 1. That's actually the operation here. Then you get the VI1 and VI1 will be then gone. And you get here VI2 minus VI2. So it will be then 2 times VI2. And you get here 2 times VIC minus the VID. That's shown here. Again, divided by 2. That's the result here. And now you see here, indeed, again, an expression for VI2. And if you look from here to ground, you actually walk that way. You see here a minus first, so we have a minus VID over 2 plus VIC again. So both inputs will have a plus VIC, and the first one will have a half of the differential mode input, the other one will minus the differential mode input, half of it. So these are the two expressions for our two input signals. Okay. The next one is a very important parameter, which is called the CMRR for short, and that is common mode rejection ratio. So what is that all about, this common mode rejection ratio? Now you might have a patient which is then lying here on the bed, and you have to measure, for example, the pulses on both hands here. And it might be coupled because of the coupling from this patients to ground or on any other conducting element here. So we have effectively here two inputs, so VI1, VI2. But there's also a connection here which is going maybe from the power from the lab, or maybe from the lamp or from the power cord or any other device that can be also coupled here. Now what happens here actually? This is a practical problem. So you see here real differential amplifiers also respond to common mode signal, which is actually what we do not want. And we also have our differential mode signal, which we do want. That's our information. So our output voltage will be then a summation of the differential mode gain times the differential mode input plus the common mode gain AC times the common mode input. So you see here the expressions and the definitions for these two. Of course, we do not want that. So that means that for a well-designed amplifier, our differential mode gain must be much, much larger than our common mode gain. And specification, as said before, we would like to use is the CMRR, common mode rejection ratio. So it is a quantitative specification that will reflect in numbers how good your rejection is. So our CMRR is defined as the ratio of the differential mode gain to the common mode gain. So the larger that one compared to that common mode gain, the better your CMRR. That is then given here mathematically as the ratio AD over AC absolute value. So we just look at the magnitude, You can also convert that in dBs by doing 20 log of that value. Let's see a simple example. Now we have a differential amplifier that has a differential mode gain, voltage gain of minus 1000. And a common mode gain, voltage gain, was minus 0.01. In this case, we would like to calculate the CMRR in dBs. Now simply we will use this formula. So the solution says actually look at the AD and AC. In this case, AD is minus 1000 and AC is minus 0.01 or minus 10 to the power minus 2. You substitute that in this formula, you get here in absolute sense exactly 10 to the power 5 or 100,000. And if you convert that to dBs, so 20 log of that, you get here exactly 100 dBs. Well, a high common mode rejection ratio means that the amplifier is much better at rejecting the common mode signal and focusing only on the differential signal which we actually want, which is our signal information. So the larger this value, the better it is. Let's see another example. So we have an objective. We would like to calculate the minimum required common mode rejection ratio. So this is a design problem for this electrocardiograph amplifier. So in this case, we have a situation here. The patient is lying there and we would like to know what the performance of our amplifier must be in terms of the CMRR for a specific situation. Now that situation is the following. We have a differential mode gain of 500 that is required. And the differential mode input signal happens to be 4 millivolts peak, quite small. But the common mode input we get from maybe from this connection or from any other connection is 160 volts, quite large, peak at a specific frequency 50 Hertz. Okay, and it is a sine wave, nice sine wave. The objective is the following. We like to have that output voltage contribution because of this common mode input no more than 1% of the output caused by the differential mode input. So that means actually the following. So the solution says actually for the desired output voltage we have is calculated from the differential mode data, which is from here and these two. So we have the VOD. This is exactly what we want. So 500 times 0.004 is 2 volts exactly. But on top of that, we will have some common mode output because of this common mode input signal. And this should be then no more than 1%. So no more than 1% of this 2 volts. That means 1% of 2 volts is 0.02 volts or 20 millivolts. This is the maximum we want. Now that means the common mode voltage gain is then this 20 millivolts divided by this 160 volts or 0.02. This is the common mode output voltage divided by the common mode input. This is the gain we want maximum for our common mode part. So 0.020 or 0.02 divided by 160, you get here 1.25 times 10 to the power minus 4. Okay, so then the required CMRR for this situation can be then calculated like so. So you know our differential mode gain, we know our common mode gain. If you now do the math here, you get here 4 million. That's our common mode rejection ratio. And how much is that in dBs? That is then, if you calculate that, 132 dB. This is quite large, and this is a performance we need for this condition. Okay, how do we determine now the CMRR practically? So we can also measure that. Now we can measure our common mode voltage gain by connecting the two inputs of our differential amplifier together and then apply here a test signal, and I call this VIC, and then measure the output here and see what the ratio is. So we apply there at both ends or both inputs the same voltage and then measure the output and then take the ratio, which is then our common mode voltage gain. Now in a similar way we will look at a differential mode voltage gain AD, and there we have two different signals which are out of phase, 180 degrees out of phase. So we apply a pure differential signal. Pure differential signal meaning actually that these two signals are 100 degrees out of phase. That should be the condition. And then we again measure the output voltage here between these two nodes and then calculate the ratio. In this case, there's a more practical way to do this. For that, this is not a problem. For this, we most often prefer to use just one source here. So you can also do this in this practical setup. So you can go for the differential amplifier here and then use only one input. Of course, this is not the exact definition, so in theory you should do that, but this is more practical. But this is only valid if your differential mode gain is much larger than the common mode gain, which is most of the time also the case. So you can use this in most cases, and it's also more practical and faster to do. So again, our common mode rejection ratio formula is shown here, and in dBs, that's the result. And these are the steps you can carry out to determine your common mode rejection ratio of your amplifier. Alright, it was our video about the differential mode amplifiers in a conceptual view. We have discussed the input sources and looked at the common mode and the differential mode operation. And from there we also looked at the very important specification common mode rejection ratio. And we also showed you a couple of examples and the simulation in SPICE to prove that the ripple is indeed eliminated using this differential mode topology in our amplifiers. If you have any questions about this example, please let me know and I will try to answer them as soon as possible. In the next videos we will discuss more details about how we can work out the mathematics from this for the BGT and the MOSFET differential amplifier. So stay tuned, and on this channel you'll see more videos already worked out in detail if you look at the channel about transistor differential amplifiers. See you next time in another video.